explaining the geometry and trigonometry worksheet. Right, if we start with a table here and a kite, think of this kite shape. If we look at the corner over here, this could be folded over directly onto this other corner on the right hand side. So there is a line of symmetry, an axis of symmetry along in the middle here. You can't do the same for the top and the bottom. We could not fold this bottom corner onto the top corner. It would not match properly. So there's just a single axis of symmetry here. So it's where we get this one here. Now for the parallelogram, it actually has no axes of symmetry whatsoever, zero. In fact, if you make your own parallelogram and try this out, you will find that if you take a corner like this, you will not be able to, well, if you try to put it onto the other corner over here, then the shape will not form perfectly onto itself. You'll be able to see some of these bits in the middle do not match properly when you do that, if you just try it out. Anyway, you can just remember no axes of symmetry for the parallelogram. Now if we look at the square, we can see that there are quite a number of axes of symmetry. You could take the corner over here and it would perfectly fold it across diagonally, and everything would match perfectly. If that corner would match over here and everything else would match as well. And same as for the other diagonal, if we took this bottom one, put it onto the top here, it would fold it directly in half. Everything would match up, all the sides would match, etc, etc. And the same thing over here, we could fold it this half, the right hand side over to the left hand side, and all in all is 4 ways of folding it perfectly. So 4 folds means 4 axes of symmetry. There's only 2 ways of folding the rectangle onto itself, so it has 2 axes of symmetry. One way of folding the isosceles trapezium onto itself is 1 axis of symmetry. Same for the arrowhead. A rhombus over here, which is a little bit like a parallelogram, but it has more symmetry because the sides are all the same. You could fold this corner down onto this corner, and there'll be a folding line there, and same way up there. So there's 2 axes of symmetry, and nothing for this irregular trapezium over here. Alright, let's get to the rotational symmetry now. First of all, I actually did the second line to begin with. This is the axes of symmetry on the second line, second row here. We're just going back to this first row of these numbers along here for the rotational symmetry, which we haven't done yet. So if you look at rotation, in fact everything can be rotated onto itself at least once by rotating it around a full 360 turn all the way around. So if you took this point, rotated it around 360, it would end up, the whole shape would end up on itself again. However, apart from that, there's no half turn symmetry. The kite simply has 1 order of rotational symmetry of 1. The parallelogram, even though it cannot be folded onto itself for axes of symmetry, it can be rotated around. If we rotated this corner all the way around, it would actually match. Once again, you could try this out if you wanted to at home. Try rotating a parallelogram that you've made around, half of the way around, it will match itself, and then you rotate it back again, full turn, and it will have an order of rotational symmetry of 2. A square can be rotated around 4 times as well, from here to here, and over to here again, second time to here, third time, fourth time back to itself. Rectangle can be rotated around a half turn over to here, and then back again to itself again, back to there. So it's a rotational symmetry of 2. A isosceles trapezium, although it can be folded onto itself, it can only be rotated around once. No half turn symmetry, it can just go around, all the way around, back to itself. So order of rotational symmetry of 1. Same for the arrowhead, the rhombus. If we think of this corner rotated around, okay, this is different from reflection of the axes of symmetry, if it would be folding. Axes of symmetry is folding, shown by these red lines, but rotational symmetry is moving it around a half turn. So if we rotated this around a half turn, it would go back onto, well, it would go onto this corner over here, and then we could do it again, another half turn back to itself. Order of rotational symmetry of 2. And odd shaped trapezium here can only be rotated around a full turn before it gets back to itself again. So it's a rotational symmetry of 2. The totals, if you total everything up down the bottom there, you'll find those are the totals there. Right, so we'll move on to reflection. Reflect the shape in the line x equals 3. Well, this line, this bold red line, in fact crosses the x-axis at 3. If we count 3 spaces from the origin, 1, 2, 3, this line is 3 away from the origin. Every single point on this line has an x value of 3, so it's x equals 3. Now notice that if we use that as a mirror line, everything matches up like this. Here you can see the R is 2 spaces from the mirror line, so R dash. Now when you draw in R dash and all of the other letters in here, you must put a dash at the end of it, and notice that R is 2 spaces away from the mirror line, R dash is also 2 spaces from the mirror line. Same for all of these other ones. Q 2 spaces away, Q dash 2 spaces away, but S is in fact no spaces away from the mirror. It's right on the mirror line, so S dash will also be no spaces from the mirror line. It's exactly on the mirror line, S dash as well. Okay, so let's move on to the next one here, y equals 2. Notice that this bold red line that I've drawn in here has a y value of 2, crosses the y-axis at 2. In fact, everything on this bold red line is 2 spaces up, has a y value of 2. So that's why we call it y equals 2. Horizontal lines are, when you say y equals a value, it will give you a horizontal line. Vertical line for x equals something. So it's y equals 2 here. Notice that P is right on the mirror line, and so P dash stays on the mirror line. Q is 2 spaces above the mirror line, Q dash will be 2 spaces below the mirror line, and so forth. S 2 spaces above, so S dash 2 spaces below. Right, next one. Reflect the shape in the line y equals x. Now y equals x is a vertical line, not vertical line, sorry, a diagonal line, y equals x. Okay, so you can just remember that that's what y equals x looks like. It's for every x value here, the y value is the same. So x is 5 up and 5 across. Same thing here, x equals y. So doesn't matter what value you go across, you also go up the same amount, and then that produces this diagonal line here. Alright, so what we have to look at is, notice that P is a short space away from the mirror line, so P dash, if you look top in this direction here, you go up and to the left, so down and to the right to find P dash, the same distance. Same way, S, from the mirror line we have to go up and to the left, so from the mirror line you need to go down and right as well to get S dash. All the same distance from the mirror line there. R dash is the same distance from R. If we draw it all in, that's what it looks like there. Okay, G has been drawn in already. Just notice that the points are the same distance from the mirror line. P is 1 space up, P dash is 1 space down, and so on. Alright, next one, rotate the shape 90 degrees. Let's bring this up here. Rotate the shape 90 degrees clockwise. Alright, clockwise is around this way, the way a clock works. 90 degrees. Now what we have to do is, if we think of everything that is away from the y-axis has to now be away from the x-axis. Notice that this point P is in fact away from the y-axis, so we think of it's about 2 high, 2 spaces up high, and it's 1 space away from the y-axis. Well, P dash is going to be 2 spaces across on the x-axis, and then you move it down 1, so it's 1 away from the x-axis in the same way that P was 1 away from the y-axis. Okay, so if we look at R, let's look at one more. Okay, so R is 1 space away from the y-axis, and it's 1, 2, 3, 4, 5 spaces up. Alright, so R dash is also 5 spaces on the x-axis and 1 space away from the x-axis. Notice that R was 1 space away from the y-axis, even though it's 5 up, and R dash is 5 on the x-axis, 5 up, 5 across. We go 5 across on the x-axis and then 1 space away from the x-axis. So we're looking at the same kind of pattern there. If you kind of rotated this around, you thought of just physically grabbing this whole image, including the y-axis, with it and rotated it around onto the x-axis, then that other image there would be a certain distance from the x-axis, just like this one is a certain distance. Everything there is a certain distance from the y-axis, right? So that's what happens when you rotate around the origin. Now things happen a little bit differently if you rotate around a different point. So here we've got the point 3, 2. We go across 3 and up 2. So that's at point 3, 2. Now we've also got to push this image backwards. It's rotated around, we swing it around in the opposite direction to a clock around that way, just 90 degrees. Okay, so if we look, for instance, at S, for instance, now we're going up 2. Instead of going up 2, we go across 2, S dash. Okay, so also R, well, R was kind of a diagonal here. Alright, 2 up and 2 across. Well, instead we're going 3 up, sorry, 3 up and 2 across. Well, we're going 3 across this way and 2 down. Alright, so it's also a pattern of 3 and 2 from the dot. We're rotating around 3, 2. Go across 3, down 2. Alright, so using that 3, 2. Think of it as an image that's kind of backwards, so you've got to make it go backwards. So every point is in the same pattern you're using. If it was 3 and 2 to get to R, it'll be 3 and 2 to get R dash as well. But obviously you're going in different directions when you do that 3 and 2. Right? Okay, here 180 degrees. Now that's a half turn around. These were quarter turns. 90 degrees quarter turn here, 90 degrees quarter turn there. 180 degrees is a half turn. Right, so it's just upside down. But you'll notice that P is 1 space away from this point. I haven't explained how you got that point there. To begin with, we've got 2, 2, so we go across 2 and up 2 to get that point there. That point that we're going to rotate everything around is 2, 2. Alright, so P is 1 space away from that point, and P dash is also 1 space away from that point. Q is 2 spaces up, and we've had to go across 1 as well. So we think of the 1 and then 2 to get to Q. Well, in the opposite direction, 1 and then 2 down to get to Q dash. Alright, and so on. Okay, so we got R, we had to go across 1 and up 3. Well, we go across 1 in the other direction and down 3 to get to R dash. Alright, same thing over here, but we've got a different point, and because we're rotating this a half turn, it's kind of similar, but it's around the point 1, 2. So rotating it around a different point. 1, it means you go across 1 and up 2, so it's right on. In fact, we're rotating it on this point P here. Okay, so P dash does not change at all because we're rotating right on that point. Alright, so when we look at Q, we had to go up 2 from there, from that point of rotation right there. I haven't actually drawn the point of rotation, and I should have drawn it in really, but it is in fact that point P right there where I've got the little mouse mouse right there, and Q is 2 spaces up, so Q dash is 2 spaces down. R is 3 spaces up, so R dash is 3 spaces down. And if we look at S as well, S, you'd have to go from that point there, up 2, across 2. So instead, down 2, across 2 in the other direction, and we get S dash. Alright, make sure you actually label everything as dash, right? The new points, you've got to have a dash after them. Okay, next one over here, translation is simply moving things, it's not rotating things. So you've got to remember here that this is how far across we go and this is how far down we go. So across 3, if we looked at R to begin with, we go across 3, down 2, and then you get R dash, you put it there. It's very easy there. So it's probably a lot easier than rotation there. So S is, once again, we're moving it across 3 and down 2. So remember 3 here, across, and down 2. Negative, it means down, alright? And if this was negative, it would be in fact backwards and left direction, which is worth look at that one there and see what that one does there. But first of all here, going at 3 and 2, so across 3, let's look at the point Q. So we're going across 3 and down 2 to get to Q dash, etc, etc, right? Okay, next one, translate the shape by the vector -1, -2. It means we're going to go backwards in the left direction, -1, so back 1. And then we're going to go up 2. Okay, so we started with R. To get to R dash, we go back 1 in the left direction, then up 2 to get R dash. And you do it for all the other points as well. And you can draw in the figure after that. Make sure you do actually draw the figures in for everything that we've done so far. You need to draw it in, not just do the dots. So it's pretty obvious, I guess. I need to mention it though, just in case. So what we've got here, enlargement. Now this is something here where the figure has to be twice as large. Okay, so all sides should be twice as long. Now if we start at the marked dot, which is at Q, then Q will not change because it's right at the dot of enlargement. It's right in the same space. So, but S will be, in fact, S is 2 spaces from the dot, the center of enlargement. So S dash will be 4 spaces, double the distance from the dot as S is. So, all right, and R is 1 space up, so R dash is 2 spaces up. P was 2 spaces down, so P dash is 4 spaces down from the dot. Okay, so same thing over here. If we've got a different dot, now we have to look at how many spaces each point is from the dot. So R is 1 space from a dot. R dash should be, we're using a scale factor of 3, see 1 to 3. So we're making it 3 times as big. So if R is 1 space from the dot, then R dash should be 3 spaces from the dot. So we count from the dot, don't count from R. Don't make a mistake and count from R. We count from a dot. So R itself is 1 space from a dot, but counting from R again, counting from the dot again, we've got 1, 2, 3 spaces to get R dash. Alright, so counting from the dot again to get to P, we've got 1, 2, 3, 4. So if you triple that to get 12, count from the dot again to get 12 spaces from the dot to get R dash. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 to get 12 spaces to get P dash. Okay, so I think you get the idea here, and obviously when you draw it in, each side has to look like it's 3 times as long, and you can check that as well and see each side is 3 times as long. So we could just look at S if you like here. We can see that to get to S here, I had to go across 2 and down 2. So triple that is going to be across 6 and down 6. So 1, 2, 3, 4, 5, 6, and then down 6 as well will give us S dash. Right, so I think what I will do is perhaps post this as a separate video and get to the next video doing explaining all of this other stuff here.